Hello, everyone, and welcome to the online training workshop. Today and over the next few days, we'll be focused on really thinking about how we can understand climate information, models, and dashboards, and particularly thinking about how we can use some of this information for health planning. This training session is really led by the Department of Climate Research from the Center for Climate Research Singapore, but is also co-hosted by the Asia Pacific Malaria Elimination Network, Climate, Environmental Change, and Malaria Interest Group, as well as us here at the National University of Singapore in the Climate, Environment, and Health program. So just to give a quick overview of some of the housekeeping rules before we get started. For all of the participants, your audio and video will be disabled, but we strongly encourage comments in the chat box, so please do feel free to introduce yourselves in the chat box. And if you have specific questions, if you can put this in the Q&A box. So there's kind of two boxes within this. So if you see other questions that you really like in the Q&A box, please feel free to upvote these, and we will have time for the speakers to answer these questions. So for all of the presentations, this will be followed by a moderated Q&A session, so we will have some time to explore these questions. And for those of you who are interested in the certificate of attendance, this will be awarded to participants to attend for a minimum of 60 minutes for all 3 days. So you will receive the certificate by email. So we will be following up. So just in case any of you are new to the Asia Pacific Malaria Elimination Network, to give you a really very brief overview of what we're trying to do. The APMEN network is a group of 22 ministries of health and over 50 partner institutions that are really focusing on thinking about how we can support malaria elimination and how we can better support vector-borne disease control programs across the Asia Pacific. Across this network, we really think about what are the impacts of climate and other environmental changes on malaria and vector-borne diseases in the Asia-Pacific region. We're particularly focused on thinking about how we can support malaria and vector-borne disease control programs to adapt to this changing environment. And finally, we're thinking about what are the opportunities for malaria and vector-borne disease control programs to actually mitigate climate and environmental changes and to advocate for kind of reductions and mitigation of climate change. So as part of this initiative, we've been really trying to build much stronger links with climate modeling groups across the region, and we're very privileged to have Dr. Aurel Moyes, who will be leading the training today to really give us an overview, stepping back from the disease focus, but thinking about some of the key questions that we need to actually understand and address these issues about what is climate change, and how can we use some of these different sources of information for our work. So with that, I'll just briefly flag that we have another webinar that will be coming up in the next week. So if you're interested in this topic, please do stay tuned. We'll be sending around announcements by email, but we'll be thinking about specifically about how we can use some of this different types of information. So with that, I will hand over to our colleagues at the Center for Climate Research Singapore, and Dr. Aurel, over to you. Thank you very much.
Thank you, Kimberly, and thank you to the organizers of this, NUS and APNM, to invite us to give this presentation on climate science. Hello to everyone across Southeast Asia and beyond, and I'm just going to share my presentation first, so give me a minute. I assume everyone can see this now, and so we will take you through 3 days of sort of a basic understanding of climate science and climate change science, followed on the 3rd day by a very practical focused session around how to use the data in impacts, especially health sciences. And so what we're going to do over these 3 days is today we'll talk about in introduction to climate science in 2 sections. that are each 45 minutes long, and we'll have a Q&A in between as well as at the end, and a 10-minute break for everyone just to have a pause and collect their thoughts before we continue. The same will happen on the following days. Tomorrow we'll focus on climate models and projections, and on the third days we look into using climate information and data. So the third day will be delivered by my colleague, Dr. Jianjun Yu, who's very much involved in the analysis of our climate information. So I've got 2 or 3 slides at the beginning to give you an idea of who we are actually at CCRS here, the Center of Climate Research, as we represent the Meteorological Service Singapore as their research pillar. So aside from us on the Center of Climate Research, we also, like most standard Met services, have a services division, observational and systems divisions, as well as business and strategic division. We are based in Singapore, so our mission is to advance scientific understanding of tropical climate variability and change and associated weather systems affecting Singapore and wider Southeast Asia region, but not just in an academic focus, but we really want to use this expertise to benefit decision makers and the overall community. So we strive to be a world-leading center on tropical climate and weather, focusing on Southeast Asia, and CCRS has been around for 13 years now. In my department, which is Department of Climate Research, we're focusing on different timescales. So we're looking at sub-seasonal to seasonal, seasonal predictions, of course, like the ENSO watch in the middle. But we're also very involved in regional ASEAN-focused forums and workshops. For example, the Climate Outlook Forum across ASEAN is coordinated here through CCRS. On the longer climate change timescales, we develop very high resolution regional climate change projections for the entire Southeast Asia region, as well as even higher projections for Singapore in the immediate domain. And I will speak about this later on when we discuss further climate projections. As such, we are very interested in understanding and doing more research in general on tropical climate processes and extremes, and talk to our neighbors in Southeast Asia and discuss and engage with the community. We have a strong focus on climate change impacts. So we look at sea level rise across Southeast Asia and other impacts around food security, urban climate change, and of course, vector disease, climate suitability across Southeast Asia. We are supporting our national efforts and our ministries in enhancing their understanding. But in general, we're quite active on communicating our science to the outside world, whether it's through scientific publications or otherwise. And I'll talk more about communications later. So this was just a short showing and sharing on who we actually are. And so now I'm going to start off with the fundamental basic understanding of what is climate variability, and then what is climate change. So, of course, in our region across Southeast Asia and what we call the maritime continent, we have very active what we call climate phenomena. And most of you would have heard of some of them. So, for example, the El Nino and Southern Oscillation, the Indian Ocean Dipole, but some of them might not have heard about others. They're like the Madden-Julian Oscillation or the Intertropical Convergence Zone, which basically defines often the position of the the monsoon as it on its journey in the year across the equator, north and south. So a lot of the times in our presentations, I show this picture to try to enhance the understanding that we live in a very, very active region here in Southeast Asia, the maritime continent, exposed to climate drivers at different timescales. So we have tropical cyclones that act on in the matter of days. The Madden-Julian oscillation travels across eastwards across the tropical area in a time of around 30 to 80 days. We have squall lines that impact this region in also on timescales of days. But the monsoon that travels between the red line and the blue line every year up and down is, of course, a seasonal propagation across the equator. So these are longer timescales, and with it, it brings specific atmospheric circulation patterns or winds that are either from the northeast or the southwest, depending on where the monsoon sits. So with this background on the various climate drivers, understanding historical and future change in the key atmospheric variables, it is often related to how these climate drivers are changing as well. So if you think about weather or climate, short time scales or the longer time scales, what actually is the difference? And often is what we say is where climate is what you expect and weather is what you get. So weather is what's happening now and here, whereas the climate is made up of statistics of weather over time. So say over a month or over a season or over a year or longer. And so you measure weather and meteorological observations like wind and temperature, atmospheric pressure, clouds and rainfall. Whereas when you look at climate, you look at the statistical treatment of these observations. So what is the average temperature of a season or a month, or what is the probability of heavy rainfall? How does it change over time? So this is a fundamental difference between weather and climate to understand the difference on and what we're talking about today mostly is climate. So climate is what you expect as a statistics, and weather is what you get. Now, climate is constantly changing. We know this. So and it varies or changes on all time scales. So whether it's what you're looking at months or seasons or years or decades and centuries, but it also varies on times and spatial scales. So the climate in across say Indonesia is a different climate to the climate in Thailand or further in the Northern Hemisphere or Australia. So we know it varies. And also if you look at really long time scales, like what we call geological time periods, then we know the climate already has slowly evolved over these thousands and thousands of years. And we actually we have records of this as we can drill into the ground and evaluate what happened thousands of years ago in the climate on Earth. Now, the actual instrumental record is not that long. So in mostly maybe since 1850. So we're talking about 170 years or so that we have evidence of this rapid evolving climate system. And when we look towards the future, we only really have our climate models to understand how this is going to happen. And I'll talk about how to model the climate at a later stage in this training. And often, if you look at the modeling of the future for longer timescales, you need to understand and set out scenarios of how the future is changing in terms of greenhouse gases, aerosols, or the changes to our land surface. So the entire Earth system is constantly responding to changes in the climate, either natural or man-made, and we'll talk about both of those differences soon. Just want to highlight that the science of climate and earth sciences integrates very strongly with economics. So as a lot of the findings from this research allows policymakers to weigh options and outcomes and do cost benefits analysis. And so our climate models are increasingly used together, coupled with economic models, looking at shared socioeconomic and emission pathways, understanding what a future for humankind may look like, and therefore informs debates on the trade-off between mitigation and adaptation. That is, of course, for every country, a national decision that they have to make in terms of how much they invest in mitigating climate change or adapting to climate change. Now, for this, essential is that we have good science reports, and that these science reports remain apolitical, but rigorously reviewed and policy relevant, not policy prescriptive. And of course, a perfect example for this are all the IPCC assessment reports over the last decades. So climate change is a very complex issue, disciplinary and relevant to many areas of our technical expertise. So we see that we have the duty to inform the entire community about what the science says in terms of how the climate is changing. Let's start to look into what we call the Earth system. So we know the Earth system is a very complex beast, and all I want to do here is maybe point out a few things that are related to this figure that you see on the right-hand side, that has a lot of areas connecting the different parts of the climate system or the Earth system. But central to this is you have to understand there is the atmosphere, the land, the oceans, the ice, and the biosphere, and all of the parts of them are interconnected in different time scales as well. So we have the atmosphere with actually very fast moving parts, much faster than the ocean, and all the water bodies together with the oceans form the hydrosphere. The ice sheets, sea ice, snow cover form the cryosphere. All the vegetation, soil, and the corresponding albedo is from the land surface. The biosphere is the life across the different components, and the interactions and connections between these different components, whether they're physical, chemical, biological, and processes that connect these different systems. So it's an enormously complex interactive system. Now, behind it all, of course, is the sun's energy that provides us with a comfortable living condition. And so I just want to highlight some things here. And so because you all know about the greenhouse effect. So the Earth has an atmosphere, and without the atmosphere, and the sun would only be able to warm the Earth to about an average temperature of minus 18 degrees, which is about the same as your freezer at home. So what the atmosphere does, and this is the greenhouse effect, is that the gases the inside the atmosphere, greenhouse gases like water vapor, carbon dioxide, and methane, are trapping reflective radiation back upwards, and thereby heating up the atmosphere to provide a much more stable, comfortable temperature at around 15 degrees Celsius averaged across the entire planet. So this greenhouse effect is making us being able to live on Earth. And what global warming is then, if that greenhouse effect is further enhanced by additional greenhouse gas concentrations and emissions into the atmosphere. But otherwise, the greenhouse effect is the standard greenhouse effect is what makes us able to live here comfortable. So what happens, and so some of my slides, you will see some more complex figures, but I'm not talking actually through all of these figures. For me, the key is to have sort of some fundamental understanding on what actually happens. You know that for example, the Earth is actually tilted its north-south axis by about 23 degrees relative to its orbital plane around the sun. So as it travels around the sun, we have the sun's energy coming onto our Earth in a slightly unbalanced way because the actual equator plane is slightly tilted. And so what happens is the equator receives a lot more energy from the sun than the poles. And so therefore this initiates some really large scale transport movements from the equator towards the poles, building these huge circulations in the atmosphere from the equator polewards and transferring that energy back again to balance the imbalance, the initial imbalance. So in Southeast Asia, of course, being in the tropics, we're actually underneath that central part where a lot of the energy is being moved upwards high into the atmosphere and then towards the poles. So this is the sort of the tropical tropical circulation. And the tropical meteorological equator then defines what is called these sort of convergence zones, where the monsoons moving up and down depending on which season it is in the year. So that monsoon defining intertropical convergence zone moves to sort of north 23 and south 23, roughly between the two maximum positions. And that's what, of course, gives Southeast Asia the monsoons, the winter and the summer monsoons, as this convergence zones every year moves north and south across the equator. So this is sort of in the atmosphere, some of the sort of large scale energy redistribution, big circulations. Now, what happens if there's additional energy being trapped in the atmosphere because of greenhouse gases? Then, of course, that circulation has to respond in some ways to this. And so we know that the enhanced greenhouse effect through additional greenhouse gases in the atmosphere is affecting these large scale circulations, and this is what we see in our simulations as well. Of course, in the ocean, you have something very similar, but on a different time scale, because the ocean is a very slow-moving, large body of water. So as water is warming in one way, it takes years and years until that energy is distributed across. So you have these large-scale ocean circulations. So you see on the bottom left figure, for example, some of the key large-scale circulations around the globe, and blue indicates that there's on the bottom cold waters, and red indicates the more near surface, warmer waters that are being redistributed across the globe. And this is on timescales of 20 to 30 years, the deep water circulation, sometimes also called the ocean conveyor belt, because these are massive energy circulations through the ocean basins around the world. And so, and of course, in being so slow, that there's a lot of the actual memory in what happens in both the atmosphere and the ocean is being captured by these large scale circulations in the ocean. So In terms of climate variability, uh, climate variability, of course, means that how the climate is varying on various timescales. And in general, what we say is this can happen because there is a forcing on the outside that drives this. So, for example, the rotation of the Earth of the Sun creates the season, and that creates the differences in the climate that we can see in each season. That can be very quite strong if you're somewhere in the northern latitudes, or not as strong if you go further to the poles. Now this, or you have variability of the energy of the sun. So we know the sun itself is not a stable emitter of energy. It also oscillates in terms of its strength every 11 years. And I'll say something to this in a minute. But this climate variability can also be generated internally, and not just from something from the outside. So for example, we know that weather, for example, has an inherent chaotic component that can't be predicted, and that randomness is always going to be part of weather. And so over a period of time, you won't be able to do long-term weather predictions, because the randomness or the chaotic part of the weather will take over. And that is actually generating internal variability of the weather, and therefore in statistics also over the climate. Apart from this, what we call the random internal variability, we also have natural modes of variability that are also internal in the system. So, for example, the El Nino Southern Oscillation, or ENSO, that is a internal interannual mode of climate variability that switches between phases. And El Nino, La Nina, or the neutral phase, that is also what we call a natural mode of variability. And so is a variability on much longer timescales that we call the decadal variability. So on timescales of 5 to 10 years. There's one that is identified in the Pacific Ocean. It's called the Inter-Pacific Oscillation, or the Pacific Decadal Oscillation. That is an oscillation in the Pacific Ocean that happens on very, very long timescales. These are variabilities in the system, and not forced by the outside or of the Earth. So in general, part of the observed variability we understand, and there's a lot of research published in this, but there's still a lot that we don't quite know, probably, possibly to the extent that we should. And part of the reason, of course, is that we often don't have all the observation necessary to study everything, especially when it comes to the longer time scale oscillations. If we only have 150 years or so of observation, then it's difficult to understand things that are even on longer time scales than that in the past. This is just showing again the relationship between the spatial and temporal timescales on these climate variabilities. So on the vertical axis are the different timescales in hours. So we have 1 hour, 1 day, 1 week, 1 month, 1 year, and so on, and even shorter ones down to 1 minute. And then we have on the horizontal scale the the actual spatial scale in kilometers. So you have 1 kilometers, 10 kilometers, and thousands of kilometers. You see on the right-hand side the size of the Earth's circumference all the way. Now, in between, you see in the atmosphere all the different processes that happen at the different time scales, and therefore at a specific spatial scale, as its lifetime only interacts over a certain spatial domain. So for example, monsoons is on the top here in blue. That happens on a seasonal time scale, so multiple months, and that affects spatial time scales of up to several thousand kilometers. So this is a nice visualization of how some of the key processes in time and space relate to each other in the atmosphere. And of course, we can do the same in the ocean. I'm not going to explain this really complex picture here, but to understand that the ocean is just as complex in terms of what processes on which temporal and spatial scales operate. But we know in general climate change works on the long time scales and the broader spatial scales. It affects the entire planet and is on hundreds and thousands of years. So I just wanted to, in with this sort of climate variability, wanted to maybe explain one specific internal mode of climate variability, which is called the El Nino Southern Oscillation, which is one that is strongly affecting this region in Southeast Asia, and where a lot of Met services also focus on predicting and notifying domestically on what sort of state of ENSO we are in. And the key reason is because it affects our rainfall. So the flood and drought behavior is very strongly modulated by what phase of ENSO we are in. And so there's three phases. The top right shows the neutral phase, where the temperatures in the surface of the ocean in the equatorial Pacific is such that there's a cool pool on the eastern side and a warm pool on the western side, with average strong trade winds that is underlying that large scale atmospheric circulation over the top, typically bringing rain over our maritime continent region, and a subsidence regime over the cool pool of the ocean where there's less rain. So that's the natural state. Now, what happens in an El Nino is that the ocean heats up much more strongly on the central and eastern side of the equatorial Pacific, pulling away the rain regime from our domain in Southeast Asia, leading to more and higher probability of droughts in our region. Whereas in a La Nina phase, the cooler oceans in the central and eastern Pacific push even stronger convection and rainfall over our region, and therefore the probability of higher than normal rainfall over Southeast Asia and the maritime continent during La Nina is typically the case. So this interannual climate variability, rainfall, droughts across Southeast Asia, ENSO is a very strong driver of this, and you can always look towards ENSO if you want to understand what's the likelihood of above or below normal rainfall, or above or below normal temperature on monthly and seasonal timescales. So here, the differences in the rainfall regimes have global impact in above and below normal rainfall. And you can see, so sort of during El Nino, as I said, our region here in Southeast Asia has impact of larger than average dry periods and larger than average wet periods across the central Pacific, but the impacts are actually globally felt. So you can see the green is where it's wetter than normal, and the beige it's where it's drier than normal. During La Nina, we have enhanced rainfall in our region and drier regions elsewhere due to these phases. So you know, probably at the moment we're heading towards an El Nino, and indicators say that it's likely to be quite a strong El Nino. So we are heading towards a phase where the left-hand side is a likely impact regime over the coming months. So climate change versus climate variability is a time scale issue. Climate variability has an impact on global warming because we know that phases like El Nino and southern oscillation is driving variability over annual timescales, and therefore global warming will interact with these modes of climate variability. And climate variability and climate change are intertwined. So, so that you always have to, if you want to understand climate change, global warming, you also have to understand climate variability, looking in the past, how the climate is varying, and then what is happening to climate variability in the future. So what causes climate change? Um, so in if you look at it really dry, we could define climate change as a statistical significant difference over an extended period of time. So if you don't look at actually what causes it per se, but how would you define a changing climate in terms of a significant departure from the status that we're in right now. And so these changes are usually in the mean, in the variability or frequency of extremes. And in fact, often we see the extremes being the first signposts of a significant change that is related to overall global warming. Now, what is important is that this difference has to be taken from a reference period. So all of the IPCC assessment reports have a baseline period that is defined, so a 20-year period that they define as a reference period, and all the differences are then assessed against that reference period. So a typical standard sentence from IPCC would say there's been a 4 degrees increase under this scenario in the future compared to the baseline period, the reference period, some reference period. So having a defined reference period is essential. Now, this climate change can be due to natural processes. So this is this internally generated multi-decadal variability, say what happens in the oceans, or it can be external natural forcing. So, for example, tectonic movements, volcanic eruptions, earth movements, asteroids, all of these external natural forcings will change the climate. And so this is not man-made climate change. But when we look towards the human influence, so this is anthropogenic forcings, this is where we actually change the climate through increases in greenhouse gas concentrations, emissions of other atmospheric pollutants, aerosols, but also modifying the land surface. So if we change how we use our land, including urbanization, all of these lead to anthropogenic climate change. At this stage, I want to invite everyone to provide some questions, and so I asked Prof. Kimberly to come back as a moderator, and we'll spend about 10 minutes to do a Q&A session here.
Excellent. Thank you so much, Dr. Orel. So we have some fantastic questions. If you have other questions, please do put them in the Q&A box. This is your opportunity to ask a climate scientist. So I'll start with the first one, who's actually from a colleague of ours in Malaysia, Wykit, who asked a question that we have been struggling with as well, which is regarding to the climate anomalies. How do we identify which indices, for example, MJO, El Nino indices, best represent the El Nino, La Nina events and other anomalies in Southeast Asia? So I think the question is about how do we pick the best indicators for our kind of outcome of interest?
Yes, so at any point in time, and we're talking about what's happening right now, I think the question is about. So you can check, for example, today you can check what is the answer doing right now. what is are we in which phase of ENSO are we right now? And are we in a neutral phase or we're heading towards an El Nino phase? Then there's a similar indicator for MGO. Is the MGO currently active in our region? You can look this up. So there's website where you can see is there an active MGO traveling across Southeast Asia or the maritime continent right now? And if you have say two of those indicators happening at the same time and they actually modulate each other, you have to see which one points in which direction. So for example, the Madden-Julian oscillation, when it travels through, leads to enhanced rainfall. At the same time, if we're in an El Nino phase of ENSO, that usually suppresses rainfall in here and will weaken the impact of the MGO coming through. So the key is to look up which of these drivers are active right now over which directions they're pointing towards in terms of enhanced rainfall, enhanced temperature or not.
Excellent. And along that question, as it's very topical in the news, do we have evidence for the occurrence of El Nino this year? So, what are those indicators telling us now?
Yes, there's very strong evidence that we are looking towards an El Nino being on the horizon. So it's very likely it will happen. And so when it comes to El Nino, uh, most Met services in all the countries in the region. So for example, in Singapore, definitely if you go there, has an ENSO watch that will tell you what is currently the state and what is planned in the next 3 months. So, for example, there's this website from the ASEAN Specialized Meteorological Center, and on that website you will see the ENSO watch, and this will tell you not only what is currently the case, so we are in a watch phase, but it will also tell you what is predicted in the next 3 months. And these predictions of what is happening with ENSO are not just done by us. They're done by a group of global centers of seasonal prediction modeling places, and all of these models come together and they form a consensus on where what we will see in the next few months. So there's actually very good evidence on this right now that we will be heading towards an El Nino.
Excellent. And we can try and put some of the references as well in the chat box because I saw there was a few questions about where to find these links.
Yeah.
There's also a few questions. I think this is a good point to clarify about the difference between climate change and climate variability. So, can we treat these as interchangeably or different? And how would we define these?
Yes, so climate variability is the behavior of the climate on a how it's varying on a day-to-day basis, either on all timescales. So the climate varies from season to season, from months to months naturally. And even under climate change, so if the world is warming up, it there will still be climate variability. But because the world is warming up, it will change the amount of variability on top of the global warming, but it may also change what causes the variability and either make it more variable or less variable. So, for example, we say in general, and IPCC says this, is that we look, climate change will lead to more extreme events. Now, more extreme events means that the variability is moving higher up and down, because only if you see more variability will you see more extreme events on either end of that varying climate. So they're completely interlinked. You can't sort of separate them, but you can analyze them separately and understand how they affect each other.
Yeah, excellent. And alongside, this is a really nice question from Victoria Cox. Um, Considering this kind of randomness and chaos and kind of climate variability, how can researchers account for this? How do we account for uncertainty in the estimates? And in particular, how does this affect communicating our results to policymakers? So I know this is quite a challenge.
Yes. Yes. So randomness is inherent in the system. And so I think one really important point to understand for the policymakers, stakeholders, government, for everyone is that when we talk about uncertainties, it's not that because we don't know how to do a better job, or that something is wrong, or there's an error in our calculations. But often this uncertainty has a very good reason. So the randomness in the weather is one reason. There's other reasons, and I will actually talk about the sources of uncertainty in more detail later on. But we need to understand that uncertainty per se is not a technical problem. It's something that we have to live with, and we actually live with every day with uncertainties in other areas of our lives absolutely comfortably. So we make a lot of decisions every day because there are certain things that are uncertain, and we make probabilistic assessments to behave in certain ways because of uncertainties that we accept to be there. Now, this uncertainty of the weather to be partly chaotic and can't be predicted. That is one of those things that we can't get better or get away with. That's just there. So we have to accept this as part of the system. That's why we're moving towards a probabilistic language in terms of projections or even in weather forecast. That's, what is the probability of this to happen, or yeah, not have just one number in terms of what the changes is, but there'll be range of change. In terms of communication to the stakeholders, one is to understand the probabilities. So this is one concept that needs to be communicated, is to understand probabilities that if you look towards a future climate, there is not one future climate that we can predict now. We can only project future climates, and that every simulation that is being done is actually a possible future climate. So we can have lots of different future climates depending on what our path is in the future. And therefore, we usually have a whole range of possible future climates that we can end up in, depending on our choice of emissions, depending on our choice of electricity distribution, our choice of demographics in the future. So there's many different pathways that will all create possible future climates. And our only way to communicate this at the moment is by providing a range that has probabilities attached to it. So that the communication issue is absolutely non-trivial. That is clear, and you have to target the communication to the audience. So if you speak to policymaker, it's very different to when you speak to the impact scientists or to others to try and communicate uncertainties.
Yeah, excellent. I think that's a really important point.
Yeah.
And just conscious of time, because we'll take a quick 10-minute break. There are quite a few questions about health impacts and about where to access different data sets and what are the impacts of greenhouse gas emissions. So I'm going to leave those now because I know we're going to touch on some of those topics later. But if you have additional questions, keep putting them into the Q&A box because we will come back to these later. So at this point, I think we're going to take a quick 10-minute break and then we'll start the second session at 2 p.m. Singapore, so in 10 minutes time. And
Yes.
thank you all for the really active engagement. It's been great to see all the introductions going on as well. And
See
thank
you
you,
in
Dr.
10.
Orwell. Okay, welcome back, everyone. Hopefully, everyone got a chance to at least stretch your legs. We thought it's good to take a break so we don't sit for 2 hours straight. Um, and I will hand over, so we'll continue. I see more questions coming in, so please do keep adding these. And please, if there's ones that you think we haven't answered or you really want to see answer, you can upvote these. So if you like those as well. So pick your favorite questions. Okay, welcome back, and I will hand over to Dr. RL.
Thanks, Kimberly. I'll share again. Cool. So now moving on from what we heard before about the fundamental Earth system and climate variability, climate change, I want to talk in terms of the details of these forcings that drives climate variability and change over some of the time scales. These are slides full of pictures that are there to highlight some of the scientific details, but the fundamental stories are on the key processes behind it. So first of all, I wanted to talk a bit about what is called the 11-year solar cycle. So this has to do with the fact that the sun actually emits its energy not constantly every minute, every day, every year. And so what has happened is the sun is a very organic, huge, radiating sun, star, and it's like it's breathing on an 11 years cycle where and you can see, for example, this cycle here that is currently active, and we are in this sunspot in this cycle where we were near the maximum of its output, and it's kind of going down. And so there's a variation of about 0.1% of the energy between the minimum and the maximum of these cycles. But these cycles are very regularly. So here is a figure that goes back to 1985, and you can see how regular these cycles are in terms of the output of the solar energy. Now, if we move back 2,000 years, we can actually see also that there's been a significant change in the output of the sun. So these are natural external changes to our climate because the incoming energy changes naturally, as in this case, in terms of the sun's energy. Additionally to the amount of energy that the sun is emitting and that we're receiving from the sun, there are also three other cycles that are driving key changes, natural changes to the Earth's climates. And these are all have to do with our orbit, the Earth's orbit around the sun. So first of all, the shape of the orbit of our path around the sun is shifting slightly from being circular to mildly elliptical. And so this shifts, you can see it on the top right. So there's a dashed curve and then there's a solid curve. So this shift between the shape of the orbit actually happens on time periods of hundreds of thousands of years. But because of this, it changes the distance between the Earth and the Sun, and therefore how strongly we're exposed to this, and therefore the climate that we're experiencing. The other thing is the tilt. So we know that the angle of the Earth's axis is tilted compared to the actual orbit plane, and a greater tilt means more extreme seasons, as there's certain parts more exposed to the direct impact from the sun. This happens around on a period of about 40 years, but it drives the extremes of seasons on the Earth. And then we call this the orbit wobble. So this is the if you can imagine the Earth's axis with your finger wobbling around itself, and that wobbling actually changes the timing of the seasons on timescales of between 20 and 26,000 years. Now, these changes, and especially the time periods, sound very long, hard to imagine, but they cause great changes over millennia. In fact, these are the things that drive ice ages. And because they determine the intensity of solar radiation that we receive at different latitude, it tells you where on which part, typically on the northern hemisphere, we see the strong impact of the cooling and therefore ice ages and interglacial periods. So all three cycles are called Milankovitch cycles. So the Milankovitch cycles are the key natural cycles behind the interglacial periods and ice ages over long periods of times. Aside from these orbit-related and solar energy-related changes, we also have volcanic eruptions. And so, in fact, the impact of a volcanic eruption is very complex in terms of what it does to incoming reflective absorbed radiation at various levels. So in general, when there is a volcanic eruption, we have sulfur dioxide, water vapor, dust, and ash in the atmosphere. It changes the energy balance because it absorbs or reflects incoming solar energy. It is mixed by atmospheric circulation. So as you know, the plume from a volcano moves thousands of kilometers very high up in the atmosphere. And when it's a large eruption, we'll actually see global impact, and that's sustained global impact over several years. So, for example, looking back to June 1991, one of the largest eruptions in recent history was Mount Pinatubo, and we saw a decrease in global average surface air temperature by up to half a degree Celsius over a period of 3 to 5 years. So these are significant impacts through volcanic eruptions. And then, of course, we have what we call anthropogenic emissions, greenhouse gases. And so, what we know is that there is the natural greenhouse effect, which is when the atmosphere absorbs reflective radiation released by the Earth's surface, and thereby warming up the atmosphere to allow a fairly comfortable temperature across the planet. But then we have and additional anthropogenic greenhouse gases being released by human activity. And so in the bottom of this figure, you see the anthropogenic generation of greenhouse gases. This is through energy generation, waste, transportation, agricultural activities, architecture activities, as infrastructure, and industries. So these are the key activities where produce enhancing greenhouse gases in our atmosphere. And we know the main greenhouse gases are carbon dioxide, CO2, methane, CH4, and nitrous oxide, N2O. Apart from this, of course, there are a lot of the other halogen gases that especially contributed to ozone depletion in the 1980s and 1990s. So 95% of all the infrared radiation emitted by the Earth's surface, so this is the reflected radiation, are absorbed by greenhouse gases and therefore enhancing the concentration of greenhouse gases in our atmosphere will warm up our atmosphere. But let's talk about so in terms of the greenhouse gases, especially CO2, which is the biggest greenhouse gas that we're looking at on Earth. We talk about concentrations and emissions, and so if the atmosphere is like a bathtub, then the emissions is the water flowing in, and the concentrations is the amount of water in the actual bathtub. So we're talking about concentrations first. So this is about the amount of greenhouse gases in the atmosphere and not who's emitting and how is being emitted. So if we talk about the amount of CO2, the CO2 concentrations, there are key measurement stations around the world that are recording the background CO2 concentration. So these are usually placed in locations where it's supposed to be fairly clean. And so Mauna Loa Observatory is on top of the mountain in Hawaii, very high up. There's another one in the south of Tasmania. So these are supposed to be at clean places where you measure the background mixed CO2 concentration. So you're not measuring this next to an emitting factory or something. So here we see the last 60 plus years on almost 70 years on the CO2 concentrations since the late 1950s to now, and the concentration went from less than 320 to over 420 parts per million. So this is a concentration measure, how much CO2 is in the atmosphere, so I remember when there was this big discussion around the 400 threshold. Oh my God, we're going to cross the 400 ppm threshold, and this was like over a decade ago. But of course, now we all know things are only going to go up further and further for quite some time to come. We also see, as you can see, this is every year it goes up and down, and so there's a seasonal variability in the global CO2 concentrations every year. But in general, as of May 2026, the CO2 concentration in the atmosphere is at 428 parts per million. Now, I said before, CO2 is only one of the key greenhouse gases, and the figure here on the top left is to show that over the last 2,000 years, where the concentration of CO2 in red, methane in green, and nitrous oxide in blue has been going globally averaged, and showing that over the last few decades, the strong increase, the unprecedented strong increase in the concentrations of greenhouse gases in the atmosphere, and we and of course, what this does as it warms up the atmosphere, and it creates a measure, how to measure the strength of each of those greenhouse gases to warm up the atmosphere, and that measure is called effective radiative forcing. And it is normalized for CO2 to be 1, so that we can compare all the other greenhouse gases to CO2. So if the effective radiative forcing of CO2 is normalized to 1, then methane is 28 times as strong in terms of warming up the atmosphere, and nitrous oxide is 265 times as strong over this 100-year period to do the same. Now, we of course still consider CO2 as being the key greenhouse gas because apart from this effective forcing capability, CO2 is much more abundant, and therefore it's still the key driver for warming on Earth as the amount of CO2 is much more compared to methane and nitrous oxide. So the intent of this figure is to show that the changes of the main drivers are exceptionally in this long-term context, as you can on these figures. So we talked about concentration, which is about the amount. Let's look at emissions, which is where it comes from and by how much. And if we first consider the source in terms of the sector, where does CO2 emission come from mostly? Then we see, for example, how coal and gas and oil are in orange and purple and green, really dominating the sources. The cement is actually quite a significant contributor to this. A surprise, you might say, is how much the land use cover change is contributing to this. So this is changing forests to farmland or urban usage land. So this is also quite a strong contributor in terms of the long-term trends of CO2 emission sources. If we look at it by region, and this comes straight out of the last IPCC assessment report, this is over the last 170 years by region, how much greenhouse gases were emitted in terms of fossil fuel and industry, land use and land use change, and forestry and others. We see Southeast Asia and the developing Pacific contributing to about 7.6% to the overall share of historical CO2 emissions. Another important anthropogenic greenhouse emissions is aerosols. Now, so what are aerosols? So these are tiny, actually solid particles, droplets that remain suspended in the atmosphere for a long time. They're sufficient to have an impact in terms of incoming solar radiation, how much goes through, and thereby temperature, and it actually also affects rainfall. So we have natural aerosols, naturally occurring, that is dust, for example, in deserts, ash from fires, and sea spray in the ocean, but also volcanic aerosols. And then we have man-made emissions of aerosols from industries, transport, deforestation. So the typical impact in aerosols on the climate system could be both warming and cooling. So aerosols is one of the most complex drivers of historical and future climate change, as it can contribute in a cooling way, but also in a warming way. There's also direct effect of aerosols because as particle in the air, they can therefore directly contribute to the warming or the cooling, or indirectly through interactions with clouds. And the last one I wanted to highlight here is what I discussed first earlier is land use change and urbanization. So we know the large scale human landscaping, agriculture, deforestation, reforestation, urbanization, and transportation are all changing our landscape, leading to changes in the amount of sunlight absorbed and reflected by the Earth's surface, as well as resulting in changes in hydrological cycles, carbon cycles, both very locally but also globally. So the land use, land cover changes is again one of the key drivers of climate change. So if we put all of this together and ask the question, so what contributes by how much to the overall climate change that we're seeing historically already. And so this picture typically by in all the IPCC reports, you will see a version of this. The latest one, the sixth assessment report, you see the greenhouse gases here in the top. The blue region is when it contributes in a cooling way. On the right hand side, the pink side is the warming. And then you have the aerosols, and as you can see, the bar here is both into the blue and into the pink region, both in a cooling and warming way. And you see the land use, land cover change that contributes in a predominantly cooling way. So if you put all this together, so you have CO2, you have methane, the halocarbons, nitrogen oxides, and all the various aerosols. We see the solid red bars in the very bottom all going to warming, of course. And this is the overall total anthropogenic radiative forcing that drives climate change right now. And so we see that overall total in the 1950s was just above half a watt per square meter. In the 1980s, it was over 1.2 watts per square meters. By 2011, it's already over 2 watts per square meters, and the current value is 2.72 watts per square meters. And that doesn't sound very much, but that is the extra warm energy that contributes to the observed climate change up until now. So here is the same picture again. So you have the CO2, methane, nitrous oxide on the left-hand side. You have the aerosol cooling here in green, minus 0.84 watts per square meters, and all the other bits and pieces, which contributes overall to a total value of 2.72 watts per square meter. And the consequence of just that is more than 1.5 degree global warming in the observed period. So this hopefully gives you an understanding of how small changes I mean, it doesn't sound very much, 2 watts per square meters but this is sort of globally average, drives this already significant warming, where we see already such really strong impacts on weather and climate. Now, if you think about it, so you have these extra watts per square meter coming in from man-made greenhouse gas emissions, creating extra energy in the Earth system. Where does that energy go? Now, as it turns out, 90% of that actually goes into the ocean. So there's 2.72 watts per square meter overall translates into what we call zettajoules of energy change. Now, what is zetta? You heard of kilo, mega, giga, tera, most of them. Some of you will have heard of peta, but then exa and zeta. So 10 to the power of 21 is zettajoules. That's how much energy is being was created with this extra warming in the atmosphere, and 90% of that energy is in the ocean, goes into the ocean, and contributes to warming in the ocean. But the ocean is massive, so the warming in the ocean is not as strong as the warming in the atmosphere. But it, of course, through this also created sea level change that we already observed. Now, 3 to 4% of this was in ice, melting the ice. 5 to 6% is actually warming the land, the soil, and the rock, and only 1 or 2% of this is went into the atmosphere, and that is the fraction of that energy that caused the increase in the temperature, in the surface air temperature. So this gives you sort of an understanding of how relative all of this. The ocean is a massive heat sink in terms of where all this extra energy goes. This here shows how temperature and rainfall over hundreds of thousands of years are actually linked. So the top green line is over the last 400,000 years, the change in CO2 concentrations in parts per million. And so we know this. How? We know this because we can drill into the ice cores, and every layer in the ice core is another era, hundreds and thousands of years ago, where we can understand from tiny air bubbles what was the concentration of CO2 back then in the atmosphere. So this comes from ice cores to understand over the last 400 plus thousand years what it was. In similarly, we can understand then what was the temperature like in all of these eras. And so down here, the on the right hand side of the red curve, you can see the last ice age, where it was globally near 8 degrees cooler than now. And correspondingly, as you have more or less ice in on the Earth's surface, that of course drives more or less sea level around the world. And so temperature and CO2 concentrations as well as sea level is interlinked. And if we just look at this, the last 170 years, and look at climate simulations that include human anthropogenic greenhouse gases versus climate simulations that only look at external natural forcings, these are the simulations. So you get the green one for only natural, and the brown one if you include human greenhouse gases, anthropogenic greenhouse gases. The black line is then the observed curve. So we can see that we can explain the observations of recent increases in temperature only if we include both the natural as well as the human anthropogenic greenhouse gases in the system. So this is what lets the IPCC to say statements like that is unequivocal that human influence is warming the atmosphere, ocean, and land, and the changes, these widespread and rapid changes in atmosphere, ocean, cryosphere, and biosphere have already occurred, and it's already affecting many weather and climate extremes in every region of the globe. So this figure is one of the key figures to drive home this message in IPCC. So for a summary on this part, I want to say external forcing increases the temperature and CO2 responses and vice versa. We see climate epochs, glaciation, deglaciation due to the Milankovitch cycle. So this is to do with the orbit. And some of the large downward spikes in temperature due to massive volcanic eruptions, like I showed you with Mount Pinatubo, decreasing global temperatures for a few years. In the modern era, the speed of change, not necessarily the magnitude of greenhouse gas forcing, is unprecedented. And this is really important, is in these figures where there's this view backwards for the 200 years. The last 100 years is this really steep increase. And it's this steep increase, it's the speed of change that we're seeing over the last 100 plus years. That is what is unprecedented and so dangerous, because it speaks to adaptive capacity of the natural system. And if there is no adaptive capacity over such unprecedented fast change, this is where systems will break down and significantly change. And then, of course, the gap between the oil forcings and greenhouse gas forcings is due to anthropogenic aerosols. So this is the key figure that showcases that without including our anthropogenic greenhouse gases, we couldn't explain the recent decadal increase in temperature. So what are the key signs of climate change that are typically put forward? So the key observed climate change indicators, of course, at the top we have rising temperatures. At the surface, the atmosphere temperatures, ocean temperatures, both rising. The atmosphere temperatures are rising more and rising faster. historically than the oceans, because the ocean is such a large heat sink. It will take a lot longer for the oceans to rise to warmer state, but at the same time, because it's slower, the ocean temperature will rise for hundreds and hundreds and hundreds of years, even if we would stop emitting right now. Recent years are being the warmest on record. So any report from the World Met Organizations or otherwise will say in the last 10 years, most of these 10 years have been record years overall over a long-term period. We see melting ice and snow, so significant reductions over the Antarctic sea ice. We see decreasing mountain snowpacks, as well as a lot of melting glaciers and ice sheets in Greenland and Antarctica are already observed. This is one of the key really worrying indicators, is how many glaciers are melting away, and the signs of Greenland ice sheets melting. We also, of course, measure sea level rise in many locations around the world. So oceans are rising at a further accelerating rate. So, and this threatens coastal communities due to the melting ice and water expansion from heat. Now, one thing I want to say with regard to sea level rise is there's if you're standing on the coast, there's two key items impacting your perception of a rising sea. One is if the ocean is coming up towards you, and this is the ocean's warming up and all the changes to do in the ocean. But the second one is land going down. So the actual sea level rise is a combination of what is happening to the land plus what is happening in the ocean. The part on the land is called vertical land motion, and this vertical land motion is due to many different reasons. Most of them tectonic, like earthquakes, but some of them also for other reasons. So, for example, if you have an ice sheet melting on top of a landmass, that landmass will sort of rebounce a little bit upwards, and that thereby rising that land higher up, because the weight of the snow pack on top of it is gone. So we do see sea level rise accelerating, threatening coastal communities, but we also know that some of those coastal communities are also sinking communities because of the extreme extraction of groundwater, and that is in some locations even much stronger than the sea level rise from the ocean coming up. We also see key observed climate change indicators in the change in extreme weather. So increasing frequency and intensity of heat waves is something, severe storms, floods, and wildfires. And with regard to extreme weather and climate change, there's been a sort of more recent science branch that is called climate change attribution, that looks at historic extreme events and tries to answer the question: can we understand how much of these extreme events can be attributable to climate change? And with regard to temperature, this is already a very much applied procedure, and I'll come back to this in a little bit later. We also see ocean acidification, increased absorption of carbon dioxide. So as carbon dioxide enhanced in the atmosphere, it will be absorbed more by the ocean, and that makes the ocean more acidic. And those more ocean acidity is affecting in a harmful way a lot of marine ecosystems, especially corals. Now, we also know about ecological shifts, so changes in ecosystems, earlier springtime snowmelt, shifting habitats for plants and animals, and longer fire seasons. So these shifts in ecosystems are plenty that we can already observe, and some of them due to climate change. Example here is the changes in Antarctic and Greenland ice sheet mass. So the Antarctic ice is in red and the Greenland ice is in blue. And this is over the last 30 years, the ice mass changes showing a massive reduction in ice mass because of global warming, leading of course, to that is one of the contributing components to global sea level rise. Here is the warming, the surface temperature warming over the last 110 or so years, and this is not observations. This is not model simulations, but we can see hotspots of warming mostly in the northern hemisphere. We know land warms faster than oceans, so you see the darker red and purple areas over land and not so much over oceans. We also see that there is this really interesting what's called cooling hole in the North Atlantic. And so this is an area where we don't see that part warming, but actually slightly cooling. And then there's a lot of white areas where there is no data available, which also speaks to the fact that and the importance of continuous global observing systems. We need the data, long-term data. So while this figure shows you that the warming is not uniform in space, there's some areas warming more than other areas. This one also says that warming is not uniform in time. So if you look at the left figure of the global warming signal, it shows 120 years averaged, but the right-hand figure just shows the last 30 years of that. And so that says the last 30 years warmed a lot faster compared to the entire period. And so this speaks to the fact that the warming has accelerated over the last 30 years compared to the overall time period. And this is what is shown here as a time series instead of a spatial figure. So the red line shows the land warming, and the blue line shows the ocean warming, and so you can see the land warms faster and more than the ocean, and you can also see that over the last few decades the slope has increased, and that's warming faster than in the periods before. Most of the hottest years globally since 1880 have occurred in the last 2 or 3 decades. Here's another observational figure showing the change in extremes. In this example, it shows the warm nights, and it basically shows the top 10 percentile of warm nights, and there's a statistical significant warming across our Southeast Asia region in the period since the early 1970s, and so we can see how warm nights have in general increased over the recent decades. I mentioned this before, climate change attribution. So this is trying to answer the question whether we can estimate the role climate change played for historical extreme events. So climate change attribution is focused backwards in history. So we want to look at extreme events over the last decades and assess this in terms of using special techniques that allow us to understand the extremes with and without anthropogenic greenhouse gases. Now, this analysis is much easier for temperature and very difficult for rainfall, and the reason being that temperature is a lot more homogeneous field, both in time and space. It doesn't vary as much in time and space as for rainfall. So rainfall can vary really strongly, just hundreds of kilometers apart, but also in terms of the seasons and months and years. So we consider rainfall what we call a much more noisy field, and the more noisy a field is, the harder it is to attribute a particular event to climate change. So if we therefore look at temperature and heat, we can, for example, read through a recent report by what's called the World Weather Attribution Group, and they bring out constant reports on extreme events in terms of attribution science. They have a very nice website to check. They brought out a report late last year where they analyzed the period of 12 months between May 24 and May 25 for temperature and heat. And here are some of their key findings. They found that about 4 billion people, nearly half the global population, experienced at least 30 additional days of extreme heat due to human-caused climate change. Also, in 125 countries and territories, climate change at least doubled the number of extreme heat days. And further on, all of the 67 extreme heat events that they found in that 12 months period were found to be influenced by climate change. So these are really strong statements around the impact of climate change to temperature and heat for this 12 months period. So one of the key figures in that report here, for example, is the number of extreme heat days in that 12 months period that's been added by climate change. And so you see the dark brown here goes all the way up to 120 days. So the climate change attribution has become a really strong communication tool for showing how much climate change is contributing to extreme events. So this ends the second session for today, and in general our training session for today. So I'll invite back Prof. Kimberly to lead the Q&A session. Kimberly.
Excellent. Thank you, Dr. Orell, for a fantastic session. I think I learn a lot every time you speak, so it's really exciting. We do have many questions, and there was a few that were very relevant to your last point. So maybe I'll start with one from Professor Indra, who we work with quite closely. And she's asked a bit about attribution. So how can we advocate that vector-borne diseases increase because of climate change? We know that incubation of viruses and parasites will be shorter when temperatures are higher, but how to ensure it's due to climate change? So any thoughts about how we can apply these attribution models to vector-borne diseases as well?
Yeah, my suggestion, one suggestion is to basically use the simulations that were done in the attribution analysis. So typically an attribution analysis involving doing simulations without greenhouse gases in them, and that creates a counterfactual historical world, and then you do the simulations that have the greenhouse gases as observed in it, and that creates the real human world as of now, and then you use these simulations to do your vector disease impact analysis. And that should show you different paths in terms of where you land for vector diseases, and in terms of the spatial, temporal, and other numbers on there. So I think these sort of counterfactual versus real world analysis on the impact side is what you probably need to do.
Excellent. And I think just another clarification about some of the climate change attribution terms. There's a question about, is this referring to any climate change or just anthropogenic climate change when you look at this?
Sorry, can you repeat this again? Sorry.
So in terms of climate change attribution, the question is, are you referring to any climate change, so both natural and anthropogenic, or just anthropogenic climate change?
Yeah, so most of the attribution analysis is done focusing on anthropogenic climate change, and so so basically when they, and it also looks over the historic period. So only say over the last 50 or so years where we have the data there, the observational data there to underpin and validate a lot of this. So they run in terms of simulation, the counterfactual world and the real world. And the difference is they include the anthropogenic greenhouse gases in the real world. And so that's the key difference, and that's why they can basically say how much more likely was the event, including anthropogenic greenhouse gases. So that's a typical outcome key statement is this event was 20 times more likely because of the climate change.
Yeah, excellent. And I think just touching on something that you mentioned as well, there's a question from Bangladesh, um, which is looking at climate sensitive diseases. So looking at dengue, malaria, as well as kind of heat exposures. But one of the challenges they face is that there's a shortage of weather observation data and health data around the country. So are there kind of ways that people have approached this in terms of trying to fill in some of these gaps, either for the climate data or for kind of comparing to similar settings to understand these risk patterns?
So I would assume that the question is with regard to the historical time period.
Oh, yes, historical, sorry.
Yes, and so in that case, for the weather and climate data, the answer is yes. And so what was done is they reran global models that includes all the observations that they can possibly get, and then rerun every day a weather model and put together. It creates like this 50-year long series of what is called a reanalysis. And the best reanalysis that is currently around is the European reanalysis, which we call ERA 5. And that is supposed to be the most realistic recreation of the state of the atmosphere at any point in time over the last 50 or 60 years. And so we use this reanalysis data to represent atmospheric fields where we don't have any measurements. So that could be because there aren't any, because it's somewhere high in the atmosphere and nobody measures it, or there's a time period that nobody had the instruments there, or so this is what we do, because this reanalysis is done using a proper dynamic models that is supposed to represent the Earth system. So ERA 5 is now on the health side, of course, that's much harder, right? If you don't have the data on the health side, it's very difficult to recreate data that was never measured.
Yes, that definitely is one of the challenges. But that does also answer a few other questions we had about credible links and good data sources for kind of climate data.
Yeah.
There was another question, which was a question about your perspective on climate modeling. Considering the rapid advances in AI and computing power, do you think we are entering a period of major improvement in predictive capability? Or are the biggest challenges still fundamentally mathematical and physical in nature, such as kind of nonlinear dynamics or the complexity of the climate system?
Yes, great question. And my answer in short is all of the above. So it's everything. So basically, we are entering an era of maybe enhanced predictability, but also needs to be understood at what time scale. So definitely on the weather time scales, where there's now a lot of forecast systems, AI-based driving enhancement in the forecasting capabilities. It's a different thing on climate, because in climate change, we know AI models are basically data-driven models. And the longer you run them, usually they explode after 30 days. That's sort of the standard thing. So if you want your AI system to do climate change, especially along a greenhouse gas warming trajectory, you need to actually design the systems quite differently. And we actually involve, but that's frontier science at the moment in terms of AI. Having said all this, none of the AI will work if you don't have a dynamic system that underpins it all. Because AI needs to be trained and understand the dynamic systems, or it'll be just garbage in and garbage out. So you do, and that's why I say all of the above. We use more and more AI, but at the same time, they need to be solidly trained on dynamic systems. So the dynamic understanding has to be there as well.
Yeah, excellent. And I think another question, this is quite interesting for me as well, about dynamic systems. Just curious how the decrease in temperature was attributed to volcanic eruption. Was this measured only for the 3 to 5 years where you saw this decrease, or did the measures continue beyond this period? So maybe that kind of plays to some of these dynamical systems that are being modeled.
You mean the cooling hole that I showed? Yeah. Yeah. So first of all, the cooling hole is over the ocean area. So that's the first, it's not over land. And so that makes a big difference in terms of trying to understand what processes might contribute to cooling right there. And so I said earlier that the ocean is these really small, slow-moving, large circulations where they redistribute heat. So what could contribute to a place in the ocean that is cooler over the last few decades? So that could be maybe a slow down of a large ocean circulation, for example, that we don't understand properly at the moment why this area will cool down, but it has to be connected to some key properties of the underlying ocean circulation. And there is an area of science that is evolving more and more that is called on tipping points and high impact, low likelihood events. And the slowing down of these big conveyor belt ocean circulation is one of those potential tipping points that are being researched frantically at the moment. But the problem there is because these large timescales are involved, where are the measurements that we can use to really look at this? And so a lot of this information comes from simulations where they simulate these conveyor belt ocean simulations and trying to understand, are they really slowing down? Because the a slowing down of these will have massive global impacts.
Excellent. And then I think there's actually quite a few questions in here about this relationship between land cover and climate. So specifically about if the temperature is a lot cooler in certain areas. So for example, cooler when there's green space, how much this differs, as well as kind of what are some of the mechanisms through which land use is actually contributing to climate change or kind of driving those patterns. So I guess that's a
Yes,
two-way question.
yes. So for example, the easiest example here is if you change, say, a forest and build a city. And suddenly you have what we call an urban heat island effect on top of the global warming signal, because if you replace a green forest with concrete roads and other things, these are huge heat sinks which will trap the heat that occurs during the daytime from the sun, and will release it much slower during the night than in a natural space like a forest, which means the heat will remain in an urban space at night. You see the much warmer temperatures, and it will slowly emit the heat into the surrounding atmosphere overnight. So this is where a typical example of where the change in land cover contributes to a change in the warming signal in this area.
Great. And I think just because we have a few minutes left, I will end on a very difficult question or a series of very difficult questions.
Yeah.
Um, so there's quite a few questions about climate justice and the fact that many of these countries that are experiencing some of the highest rates of warming and some of the most profound impacts of climate change on health are the countries that actually have quite low emissions.
Yes.
There's another kind of comment about some of the change in US policy to no longer use the term climate change, and kind of refocus efforts. So I
Mm.
guess it's a very broad question, but how do you see this as kind of how can we advocate and how can we kind of support, especially kind of coming from areas that are not the major emitters of greenhouse
Yeah.
gases?
Yes. These are very policy relevant questions, which as you know, for me as a scientist who is sort of policy informing but not policy prescriptive, I would certainly step back from recommending certain solutions in this space. Now, for me, climate change is a global problem and can only be solved globally. And therefore everyone has to work together. Now, historically, there's a clear imbalance in who's emitted by how much. But to me, that the solution can only be found together and not by separating out. At some stage, there's a very strong uh, economic question involved in solving this. Absolutely. And so the solution to this is at the moment in the policy arena driven by um, finding business solutions that bring countries along to help solve it together. And maybe that's the way we will solve it. I don't really know. But for me, the only way to solve it is by everyone coming together and working together and supporting their governments to support the solutions. And we know there's governments who don't. We know there's governments who'd rather focus on other things than climate change. But for us, there's no one silver bullet. It has to come by everyone working together.
No. Excellent. I think those are really kind of nice words to wrap up on. I think it's really
Mm,
important to have that strong scientific evidence. And I think the other
mm,
thing that we're really grateful for you both for spending the time here today is to actually have the links between climate scientists and people working on some of these impacts. So it's really important to kind of understand the scale of the problem and understand what people are doing about it so we can
yeah.
act. So with that, I think I will wrap up for today. We will be back tomorrow at the same time, so a similar schedule, with a kind of 2 hour session, a short break in between. Tomorrow, we will be focusing on climate models and projections, so thinking about how we can take what we know now to look at the future. And for those of you, I've seen quite a few questions as well who are interested in actually how do I link this with health data? We'll go through some practical examples of that on the third day on Thursday. So don't worry, we will kind of get to that as well. But thank you everyone for a lot of engagement, and thank you most of all for our speakers.
Thank you. Very nice. Very happy.
Right. Thanks everyone.